Hello everybody! In this video I will show you my recent work towards the ultimate trajectory tracking control. First of all, let's see the vehicle with only active front steering. Using active front steering, this vehicle realizes the trajectory tracking to pass the double lane change test. With the rising initial speed, the lateral acceleration of the vehicle is gradually reaching the physical limit, and the error of the trajectory tracking is getting bigger. As you can see on the high speed, the lateral acceleration needed to track this kind of trajectory exceeds the physical limit of the vehicle. So, in daily driving, we want to control the vehicle speed using driving or braking, so that the vehicle can pass the curves with a feasible speed. In the following simulation, we will use the rear driving and braking to control the vehicle speed and also to generate the needed yaw moment. The vehicle speed is restricted according to the curvature of the incoming trajectory in the next 1 second. We can see that the vehicle tracks the trajectory smoothly with a feasible speed. The red transparent ball is the reference position for the center of gravity of the vehicle. To track the trajectory at any speed, the FreeNet coordinate system is used. It is noteworthy that here the tracking deviation is not calculated but integrated. The integration error will be accumulated during the simulation, so that's why at the end, as you can see, the reference position and the center of gravity don't completely coincide with each other. But this won't be a problem for the real autonomous driving system. The trajectory planning algorithm there will update the reference trajectory and the initial deviation in, for example, every 500 milliseconds. The trajectory tracking can also be realized using the rear steering. As you can see, this trajectory tracking controller works with different actuator topologies. Actually, during this whole process, the structure of the controller didn't change. This controller is actually a fault-tolerant controller for the actuator topology, four-wheel steering, driving, and braking. The fault of an actuator can be considered by adjusting the parameters of the controller and the parameters of the model in the controller. The change of the parameters is called reconfiguration here, which doesn't change the structure of the controller and the model. Setting different actuators in the failure mode, and we can get different actuator topologies. If there is no actuator in the failure mode, then the actuator topology is four-wheel steering, driving, and braking. For the conventional front steering vehicles, a small slip angle guarantees the driving stability, but the four-wheel steering allows the vehicle to drive stably even with large slip angles, as you can see here. In this controller, a special design is adopted to guarantee the driving stability of the vehicle. This design works for both front steering and four-wheel steering, and also for any other actuator topologies. This design can also let the vehicle to make the full use of its dynamic potential. In the simulation, we assume that the actuator faults have been detected and isolated. With these informations, the fault-tolerant controller can keep tracking the reference trajectory even at actuator faults. Some specific actuator failures have been already demonstrated before. Now I want to show you some more general actuator faults. Now let's go back to the four-wheel steering, driving and braking without actuator faults. By adjusting the weights of controlled variables, we can change the driving style. For example, as we can see here, we can let the vehicle to drive with smaller slip angles. This kind of driving style is more like the conventional front steering vehicle's driving style. Although the four-wheel steering vehicle has the ability to drive stable with large slip angles, the passengers, however, may prefer the conventional driving style. Except the adaptation of the actuator faults and the adjusting of the weights, this controller also provides the other online adjusting functions, such as the adjusting of the restricts and the tugged values. Using the online adjusting of restricts, the dynamic reduction of actuators, which is one kind of actuator faults, can be addressed. However, this will not be shown in this video. What I want to show you here is how I use the online adjusting of target values to realize naturally the slowing down to stop and the reversing. It is noteworthy that all these online adjusting functions are realized without switch the system. All these simulations are done within one control system and within one prediction model. As you can see, this controller adopted a so-called one-piece design. It uses just one system to realize the trajectory tracking control with different actuator topologies, with different driving style and under different driving situations. The trajectory tracking control is one kind of motion control. This one-piece motion control without switch the system looks really biological, just like how the human and animals control the motion of their body. The difference is that the prediction model in the controller is much more precise than the prediction model in the instinct of human and animals. This controller also needs a brain to make the decision and to plan the motion. At the state of art, the autonomous driving is usually hierarchic structured like this. In machine perception, a lot of neural network algorithms are used, which are also very biological. My next research directions will be the realizing of a real-time nonlinear model predictive trajectory tracking controller. the addition of the obstacle avoidance function in the controller, and the integration of motion planning and control in one level. Besides, in my opinion, the realizing of the decision making in a biological way would be a really interesting topic. That's all for this video. I hope that you enjoyed it. Thanks for watching.